In this video, I introduce a deep speech model for automatic speech recognition. Deep speech is an end-to-end recognition system in which deep learning based on recurrent neural network and combined with a language model replaces surface dictate pipelines in the traditional speech recognition. An RNN model is trained to ingest speech spectrograms and generate text transcriptions. Suppose that a single utterance X and his label Y are sampled from a training dataset X. Each utterance Xi is a time series of length Ti, where every time slice is a vector for audio feature Xti, T from 1 to Ti. Spectrograms are used as features, so XTPI denotes the power of the piece frequency bin in the audio frame at time t. An RNN model converts input sequence X into a sequence of character probabilities Y hat t, where CT is one of 70 characters. The bidirectional RNN model consists of 5 layers of hidden units, where the first 3 layers are not recurrent. The first layer is a bidirectional recurrent layer, and the last layer is not recurrent, as shown here. The hidden unit at layer L are denoted as HL. For the first layer at time t, the output depends on the spectrogram frame xt along with the context of C frames on each side. Namely, this xt, we have C frames before xt and C frames after xt. The remaining non-recurrent layers operate on independent data for each time step. For each time t, the first 3 layers are updated through a function g here, where gz is a real activation function, and the WL and the BL are the weight matrix and bias parameters for layer L respectively. The bidirectional RNN layer consists of 2 sets of hidden units. Forward recurrent units HF and backward recurrent units HB, which are defined as here, where HF is computed from T1 to Ti, and HB is computed from Ti to 1. The 5th layer takes the output sum of HTF and HTB generated by the first layer as input, and his output HT5 is used as input to the softmax output layer, which generates a probability of a character K at the time t, this formulation. Where WK6 is a case column of the weight matrix W, and BK6 is a case bias. Once having predictions P, we compute the connectionist temporal classification loss L to measure the prediction error. If the model is trained using large quantities of labeled speech data, the RNN model can learn to produce readable character level transcriptions without using a language model. However, N-gram language model is combined with the RNN model to improve the model performance on the word level. And given the RNN prediction B, the combined model finds a sequence of the most probable characters C1, C2, which matches the RNN model and the language model. The goal is to find a sequence C that maximizes the combined objective Q here. Where alpha and beta are turnable parameters that control the trade-off between RNN language model and the length of the sentence. PLM is the probability of the sequence C. A bin search algorithm is used to maximize the objective. For more details, please check with these references. Thank you. Bye.